Okay, we'll start talking about some of our geometric rules. I told you before that geometry is a whole new language, and it's got its own set of rules that we have to learn to know. So we want to make sure that we're continuing to study our vocabulary and as well as learning these rules. And so a couple of different types of rules in geometry: postulates and theorems. Postulates are rules that we just accept as being true without having to prove them. And for that reason, very often postulates are incredibly obvious to the point where it may even seem sometimes like we shouldn't even be talking about them. But we need to acknowledge them so that we know that we can use them. Just kind of store them away and pull out those postulates whenever we need to. We've already talked about a couple, right? The segment addition postulate and the angle addition postulate. Again, those are a couple of things that before you looked at it, you probably didn't think about it, but once you did, you kind of thought, well, that just makes a ton of sense. So the segment addition postulate, which says if you've got a point in between two endpoints of a segment, then if you add this guy plus this guy, it equals the whole thing, which is, hopefully incredibly obvious, but something that we may not have thought about a whole lot before we talked about it. Theorems we have to prove. Okay, theorems are basically conjectures that need to be proven before we can accept them as being true, and use those rules to help us figure some other things out. Okay? Difference between postulates and theorems. Now, that being said, there are a lot of postulates that sort of set our groundwork for other things that we're going to do. And so there's a series of postulates that you need to get in here and that you need to know and be able to recognize. But the last thing I tell you to do is to memorize these numbers. Postulate 5, 6, and 7 state these. So postulate 5 says through any 2 points there exists exactly one line. Okay? There exists exactly one line. And we know that it takes 2 points to make a line. But that postulate goes a step further and says that there exists exactly one line. Okay? And postulate 6 kind of reverses it a little bit. It says that a line contains at least 2 points. Okay? And the last one, if 2 lines intersect, then their intersection is exactly 1 point. If 2 lines are going to cross, then their intersection is going to be exactly 1 point. Okay? You need to understand what those postulates say, but don't worry about memorizing the numbers. If you open up a different geometry book, those postulates will be numbered something different. So the numbers are just sort of a way to organize them in a textbook. Okay? That being said, it's helpful sometimes. Okay, but I think real-life examples or the world around you is kind of a nice place to start too. Okay? Postulate 8, 9, 10, and 11. So 5, 6, and 7 talked about lines, points and lines. 8, 9, 10, and 11 talk about planes. Okay, so postulate 8, through any 3 non-collinear points, there exists exactly one plane. So if we wanted to find an example of postulate 8, we want to try to find 3 non-collinear points, and then figure out what plane they're going to sit in. Postulate 9 says a plane contains at least 3 non-collinear points. And that word non-collinear is pretty important. Okay? So an example of postulate 9, you'd want to find a plane and then figure out what 3 non-collinear points might exist in that. Postulate 10, if 2 points lie in a plane, then the line containing them lies in the plane, right? So if I've got a plane and I've got 2 points, then without even thinking about it, I know that the line that connects those 2 points has to lie in the same plane. Okay, again, these postulates are I think pretty obvious, but we discussed them so that we can use them. And then postulate 11, if 2 planes intersect, then their intersection is a line. Okay? Think about that. If 2 planes intersect, then their intersection is a line. Okay? We got those? We'll keep rolling. So now we'll do this in a couple of different ways using some diagrams. So here's an example for you here. Identify a postulate illustrated by that particular diagram. Right? Diagram A. Which postulate is that representing, Mandy? 7. Okay? 7, which says if 2 lines intersect, then the intersection is exactly 1 point. Okay? Good. And what about diagram B, Rylan? 11. 11, which says if 2 planes intersect, then they intersect, their intersection is a line. That's exactly what it's showing. Okay? Good. And then the last one. If you have point A, B, and C there, Tova? Postulate 8, which says through any 3 non-collinear points, there exists exactly 1 plane. Okay? Oops. Good. Non-collinear. Why is that important? Why is non-collinear important? So P, if anybody look, no, you guys can't because you can't see. Why is non-collinear important? If we chose 3 collinear points. All right, good. Another way to look at this. Use the diagram here. And this isn't in your notes. So let's do this one. Then I'll give you a second to identify the example in your notes. Use the diagram to write examples of postulate 9 and 10. Right? Postulate 9, which says a plane contains at least 3 non-collinear points. Right? Then we can talk about what? In this particular picture, we can talk about plane P contains point A, B, and C. Okay? Perfect. So that would represent postulate 9. Postulate 10, which says if 2 points lie in a plane, then the line containing them lies in the same plane. So we could talk about, since point A and point B lie in plane P, then that means line N, or line AB, also lies in plane P. Okay? So, examples from the diagram to identify those postulates. Now, the one you have in your notes is this one. So, try this one. Use the diagram to write examples of these postulates. That are already written out, but the first one's not so bad. Postulate 9, example from the diagram of postulate 9, plane what? Q contains at least 3 non-collinear points, which are V, W, and Y. Makes sense. Okay, so plane Q contains at least 3 non-collinear, V, W, and Y. Now the next two, or the next one is worded kind of funny. But an example of postulate 10. 2 points. We need 2 points in a plane. So in that picture, Example of 2 points in a plane. Say again?
VW.
VW is in plane what?
Q.
Okay, so points V and W are in plane Q, right? That means, what else has to be in plane Q? A little bit of a trick question. A line, right? So line VW is going to be in plane Q. Make sense? And then the intersection of plane P and plane Q is what? I thought someone whispered it. Can't hear you. No, the intersection of plane P and plane Q is line B. Okay, the partial 11 says that when two planes intersect, they intersect at exactly one line. That's the line that these guys are intersecting at. Okay? Make sense? Excellent. Okay. You need to be able to sketch this stuff. Okay? You need to be able to sketch this stuff. All right? So if we want to sketch a diagram showing line TV intersecting segment PQ at point W so that TW, segment TW, is congruent to segment WV. Okay? It's a lot of stuff there. Right? Here's where I would start. Line TV is supposed to intersect segment PQ, right? So maybe we draw line TV. And it's supposed to intersect segment PQ at point W. So some point on this line, there's a point W that segment PQ is going to meet line TV, right? So now I need a segment PQ. But they're intersecting so that line TW is congruent to line WV. Right? So there's one last thing we need to show. We need to show that TW is congruent to WV. And then we've got everything in there, we're done. Okay? You guys try to sketch some things. Some of these postulates can be kind of tough to sketch as well. Just do the best you can. All right? Questions there? Okay. That's 2-1 and 2-4. That's what your quiz on Tuesday is going to be over. I'm going to try to push ahead a little bit here. Okay? Get through this. And talk about... one more slide here. Definitely want to talk about this. Okay? Because part of this is... part of what we want to talk about, too, is what we get to assume or not assume from a diagram. We're talking about diagrams. We want to talk about what we can and cannot assume in diagrams. So this is not in your notes. Let's see if we can't get through this anyway. Which of the following statements cannot be assumed from the diagram? Okay? Can you assume that point A, B, and F, if you can see the diagram well enough, are collinear? Why? What's that? Yeah, there's a line that actually that contains them, right? Can you assume that E, B, and D are collinear? Why not? Right, there's not a line drawn. They may look like they're collinear, but we don't have a line drawn through them to know for sure. So we can't assume that, right? So this is a yes, this is a no. Can we assume that segment AB is perpendicular to plane S? Can you see the picture well enough? Okay, Noah, you're shaking your head. Yes. Why? Why can we assume that segment AB is perpendicular to plane S? We'll help them out. Yes. This right angle box right here tells us that, right? They form a right angle, so they have to be perpendicular. Okay, and the next guy says that segment CD is perpendicular to plane T. CD is right here. Can we assume it's perpendicular to plane T? No, no right angle box, right? So again, this is a yes and a no. Now, can we assume that line AF intersects line BC at point B? Yeah, because the diagram actually shows it, right? There are things we get to assume from a diagram, and there are things that we do not. And so we got to make sure that we're not just trying to look at the picture and say, it looks like a right angle, must be a right angle. Okay? We don't get to do that. All right? All right. Oop. All right. I'm going to try to push forward a little bit here. Get into 2.5. 2.5, we're going to start writing some proofs, but we're going to do this in sort of a segue from Algebra 1 into geometry. So we need to review some Algebra 1 properties. Okay? When you were solving equations, you talked about the addition property, the subtraction property, and the multiplication property. You also talked about the division property, which we're going to see in a second. These are properties that say that tell you how to form equivalent equations. And so the addition property says if you add the same thing to both sides of an equation, then it doesn't change the meaning of the equation, it just changes the way it looks. Right? So the equation is still the same. Same thing with the subtraction property. If you subtract the same thing from both sides of an equation, then you haven't changed the equation, you just changed the way it looks. Multiplication property, if you multiply the same thing into both sides of the equation, right? So if A equals B, then if I multiply C into A and C into B, then it's still going to be a true equation. It's going to be an equivalent equation, right? So the addition property, subtraction property, and the multiplication property. All right? The division property, which says that if you divide both sides of the equation by the same thing, as long as you're not dividing by 0, because we can't divide by 0, then you have an equivalent equation, just looks different. Right? Then there was something called the substitution property that we didn't maybe didn't use as much in Algebra 1, but if A equals B, then we know that we can substitute A into any other equation or expression where B might be, right? So, and we did that a lot in the form of if X equals 4, then we know that we can go into any equation or expression in that situation and plug 4 in for X, right? We're substitution property. The distributive property. Okay, remember that. If we've got A times B plus C, then we can distribute the A. A times B plus A times C is going to be the same thing. Okay? So a lot of our properties here. Okay? It's a lot of stuff. Keep track of it. We got those in? Now, here's how we're going to use those properties in the form of a proof. And again, you guys did this in Algebra 1. We're going to review this now and let that sort of transition us into writing geometric proofs. So if I want to solve that equation, the idea behind this is I'm going to solve this equation in such excruciating detail that you guys can explain to my 8-year-old what you're doing. Okay? And if you've never talked to an 8-year-old, when you do something, she's going to ask you why you did it. Okay? So every time you do something, you've got to tell her why. Okay? So what we can do is create normally 2 columns. This one has 3. Okay? Here's how we want to approach this, right? The middle column just tells us what we're doing, right? So we start with that equation. Write the original equation. Why do we get to do that? What's the reason? Well, in any self-respecting proof, we always start with given information. That was given to us. I want you to solve that equation. I gave that to you. Okay? Because our algebra skills are well honed, we know that once we get that equation, the first thing we want to do to solve that thing is distribute the 3 and distribute the 2. Right? So we get 6x plus 3 plus 4x plus 2 plus 7 equals 42 minus 5x. And the reason why we get that, the reason why we get to do that is because of the distribution or the distributive. Come on. Distributive property. Okay? Now, once we've done that, we can now combine the 6x and the 4x. We can combine the 3, the 2, and the 7. Right? Because we're combining like terms. And I like just calling this simplifying. We're just simplifying that side of the equation. Okay? By combining like terms. From there, we want to show adding 5x to both sides. Right? And we get to do that because we know from the addition property, okay, the addition property tells us that we can do that. All right? Now, once we've added 5x to both sides, we have to combine like terms. Again, this says evaluate. Again, I like to call this simplifying. We're just simplifying that down now. Now we get 15x plus 12 equals 42. Now we know we got to subtract 12 from both sides. Right? When my 8-year-old asks why you're doing that, you can tell her, well, the subtraction property says we can. That's allowed. Okay. Then we're going to combine those, the like terms on both sides. So we're going to simplify. Okay. Then we're going to divide both sides by 15. And the division property, you've got to include the word property in here, says we get to do that. You'd see if that trial thing would go away. And then once you do that, we can simplify again, and we end up with our solution here. Okay?